This video demonstrates the use of a motion control technique called input shaping to reduce oscillation of an endpoint, such as the payload on a crane. A generic motion profile, even if it is jerk limited, can produce excessive oscillation at the payload. The easiest way to reduce oscillation is to accelerate very slowly to not excite the pendulum. A much faster motion can be accomplished if the motion profile is shaped to cancel out the oscillation. This technique is called input shaping. This is an open-loop control approach. No additional sensors are used to measure the pendulum oscillation. It's difficult to see the true shape of the profile on the HMI screen, so I'm going to record the commanded motion at a higher resolution here. The pink line is the commanded velocity. The blue line is the commanded acceleration. Open-loop input shaping, though, is sensitive to the natural frequency of the pendulum. I'll add a couple more pendulums. One shorter, and one longer. The shaped profile is not as effective for these. Open-loop input shaping is also sensitive to disturbances. If the pendulum already has a little oscillation, say from a gust of wind, the shaped profile does not remove the oscillation. So although input shaping is an open-loop approach, a means of sensing disturbances and changes to the natural frequency is usually necessary for most applications. The suitability of the input shape depends also on the target cruising velocity. The shape for reducing oscillation at 50 millimeters per second is different than the shape for cruising at 80 millimeters per second. Or 180 millimeters per second. Finally, the effectiveness of the shaped input will depend on having suitable mechanical and servo components that can accurately implement the shaped motion profile. If implementing and programming motion would be beneficial for your line of work, please follow the link in the video description for details on our motion control workshop. It provides a very rapid hands-on introduction to industrial motion control, where each participant has a system in front of them like the one in this video. The rest of this video describes the engineering work for selecting the profile shape. There are several methods for input shaping. The approach I used involves modeling the system dynamics, constructing a segmented motion profile, numerically simulating the system response to the segmented motion profile, and optimizing the segmented motion profile to minimize oscillation at cruising velocity. This setup uses an Omron 1S servo motor and ball screw transmission to control the position of a carriage. A small pendulum is attached to the scaffold on the carriage. So this system has 2 degrees of freedom, the carriage position X and the pendulum angle theta. The servo motor and ball screw provide accurate and responsive motion, and I'm treating this as a perfect positioning source. So the only dynamic equation we need is for the pendulum angle. The equation of motion can be derived using free body diagrams or energy methods. If the angle of oscillation is small, this equation provides sufficient accuracy. If we know the input motion, x of t, and the initial angular position and velocity of the pendulum, we can solve this equation and predict the pendulum's motion. This equation is linear. It has an analytical solution, but I'm going to use numerical integration with MATLAB to find an approximate solution for the system starting at rest and experiencing a rectangular pulse input for acceleration. The tail end of the response can be inspected to evaluate the final amplitude of oscillation. The final amplitude depends on the magnitude of the pulse input. The final amplitude also depends on the duration of the pulse, or more accurately, it depends on the state of the pendulum at the falling edge. Input shaping for attaining a desired cruising velocity requires a more complex profile than a single rectangular pulse. The Omron NX motion controller that I'm using has a variety of motion control instructions that use S-curve profiles. These profiles have linear acceleration ramps according to a finite jerk value. A suitably complex shape can be produced by executing a series of move velocity commands with different velocity targets and jerk values. Intuitively, after the motion begins, the pendulum will swing backward relative to the scaffold. It might be advantageous to reduce the acceleration to adjust the time that the pendulum swings forward, and then increase the acceleration to meet the pendulum at the top of the swing. Based on this intuition, a 3-segment profile should provide adequate shaping ability. By writing a motion planning function in MATLAB for a 3-segment profile, the pendulum response to this motion input can be simulated. This 3-segment profile has 6 parameters, 3 velocities and 3 jerk values, but the final velocity is specified, and that leaves 5 parameters for adjusting the profile shape to reduce the final oscillation. The optimization problem is to find the parameter values that will minimize the final oscillation amplitude. Now, there is a distinction between a local minimum and a global minimum. A local minimum is relatively easy to obtain, assuming the objective function is smooth and has a gradient. We can pick a seed point and adjust the parameters in the direction of the gradient to find the basin of attraction. It's akin to letting a ball roll down a hillside into a valley. The MATLAB function fmin_con is a good tool for optimization problems with gradients. From the output, we can see that it has converged to a local minimum, but this is not the best solution. Some objective functions have a single basin of attraction, where no matter what seed point is provided, the optimization will yield the same solution. Other objective functions may have many basins of attraction, some of which are lower than others. The goal is to find the lowest basin, the global optimal solution. This problem has many basins of attraction. Multi-start is a nice MATLAB tool for finding the global minimum. It scatters many seeds to find distinct locally optimal solutions and ranks them. The lowest value is hopefully the globally optimal solution. Now, if multi-start returns a distinct solution for every seed provided, it must be a very rippled surface. For such problems, other optimization algorithms that don't rely on the gradient evaluation might produce better results. For this problem, the particle swarm algorithm frequently finds a solution that perfectly cancels out the oscillation. Now, you can't get better than that. There's no question it is a globally optimal solution. But this is not a unique best solution. There are actually many solutions that cancel out the oscillation. Here are 3 different solutions found. So then, the problem is now how to select a solution to implement. If the number of solutions is small, it's simple to make a reasonable selection. Among these three, I like the third solution best. Although it's the slowest to reach the target velocity, it provides the smoothest motion. The velocity is monotonically increasing, and it has the least amount of oscillation during acceleration. But the full set of solutions is infinite, so a different approach for selection is preferred. One approach is to modify the objective function to also seek to minimize another aspect, such as the time to reach the target velocity. Another approach is to constrain the solution space to be smaller. One way to constrain the solution space is to pick a consistent value of jerk for all three segments. This reduces the space to 2 parameters, and the objective function can be plotted as a surface. From the plotted surface, we can see 3 local minima that produce 0 final oscillation for the target velocity of 50 millimeters per second. This surface looks like FASN-MU should be effective at finding a solution in the constrained space. Yet, it still has difficulty. If we were to zoom in on the surface at around a small point, the surface no longer looks smooth, and this explains why FASN-MU struggles relative to the particle swarm algorithm. These microripples are likely caused by the adaptive step sizing used in the differential equation solver. For this application, it would be nice to be able to optimally shape the profile for a range of cruising velocities. Here is the surface for a cruise velocity of 200 millimeters per second. Clearly, the full surface does not deform smoothly, but there are subregions that do. And this solution is present for all velocities between 50 and 200 millimeters per second. So I selected this one for implementation.